Within the central nervous system and the liver, the catechol-O-methyltransferase enzyme, or COMT, operates as a primary biochemical traffic controller. It is the engine responsible for clearing catecholamines, like dopamine and adrenaline, along with reactive catechol-estrogens. The efficiency of this clearance is dictated by the Rs4680 polymorphism, availing to methionine amino acid substitution. This specific genetic variation, known as the MET-MET genotype, appears in roughly 25 to 29% of individuals of European ancestry. This substitution changes the enzyme's structure, reducing its catalytic velocity by 60 to 75% compared to the fast-acting valine variant. This reduction in speed creates a systemic delay. Dopamine, adrenaline, and reactive estrogens remain in the synaptic clefts and systemic circulation for extended periods, rather than being deactivated. Effectively managing the 75% deficit in clearance speed is the prerequisite for preventing the chronic accumulation of these excitatory and oxidative molecules. The COMT enzyme neutralizes these molecules by transferring a methyl group to their catechol ring. This chemical transformation turns a highly active neurotransmitter into an inert compound, preparing it for excretion. For this reaction to occur, the enzyme requires two specific inputs: a magnesium ion, which acts as a structural cofactor, and S-adenosyl methionine, or SAMe, the universal methyl donor. When SAMe loses its methyl group, it becomes S-adenosyl homocysteine, or SAH. This byproduct then binds to the enzyme, acting as a competitive inhibitor that naturally regulates the speed of the clearance process. While a fast COMT variant processes this feedback loop efficiently, the slow MET-MET phenotype requires optimal cofactor availability and a precise biochemical environment just to maintain its limited baseline. Stabilizing the slow COMT pathway requires more than generic support. It demands the rigorous management of substrate loads, the targeted delivery of cofactors, and the modulation of the autonomic nervous system. The biological impact of this slow enzyme is most pronounced in the prefrontal cortex, the region of the brain that governs executive function, working memory, and emotional regulation. Unlike other brain regions, the prefrontal cortex lacks a high density of dopamine transporters for rapid reuptake. It relies almost exclusively on the COMT enzyme to terminate the dopamine signal in the synapse. The Goldman-Rekikic inverted U-curve shows cognitive performance peaks at an intermediate dopamine concentration. A fast COMT individual sits on the left side at rest. However, because the slow MET-MET enzyme clears dopamine poorly, higher resting levels shift their baseline to the very peak. In low-stress environments, this high baseline provides a cognitive edge, resulting in the intense focus, analytical depth, and robust working memory associated with the warrior phenotype. During a stress event, the adrenal glands and nervous system release a sudden flood of adrenaline and norepinephrine. For the slow COMT individual, this stress hits a dopamine-saturated system, pushing their balance off the peak and down the curve. The enzyme cannot clear this flood, resulting in an executive shutdown, somatic anxiety, and an inability to return to baseline. This overload is amplified if the individual also carries a mutation in monoamine oxidase A. When the MAOA pathway is also slow, both the primary and secondary clearance systems for excitatory neurotransmitters are bottlenecked. This compounded phenotype requires the strict avoidance of high tyramine foods, like aged cheeses and fermented meats, which trigger a massive release of norepinephrine that the system cannot process, potentially leading to hypertensive spikes. For a slow COMT patient, a momentary stressor can trap excitatory molecules in circulation for hours, turning their cognitive depth into a period of prolonged autonomic distress. In the liver, the COMT enzyme acts as the non-negotiable bridge for phase 2 detoxification of endogenous estrogen. Phase 1 metabolism splits estrogen into two paths. CYP1A1 produces protective 2-hydroxyestrogen, while CYP1B1 creates the genotoxic 4-hydroxy metabolite. These must be methylated in phase 2 to become inert. In slow COMT, delayed clearance causes toxic 4-hydroxy metabolites to stall and recirculate systemically. This buildup drives clinical symptoms of estrogen dominance, including heavy menses, uterine fibroids, and cyclical mood instability. Estrogen itself further complicates the bottleneck, as systemic estradiol acts as an epigenetic downregulator of the COMT gene, suppressing the expression of the very enzyme needed to clear it. Standard blood panels measuring total hormone output will often show normal levels, missing the accumulation of reactive metabolites occurring at the cellular level. A significant threat to managing this phenotype is the accidental introduction of competitive inhibitors through common supplements and plant-based foods. This catechol structure, a benzene ring with 2 hydroxyl groups, is prioritized by the COMT enzyme. Antioxidants like quercetin and EGCG share this exact shape. When ingested, they act as competitive substrates, occupying the active site and preventing the clearance of endogenous dopamine and estrogen. Individuals with slow COMT should avoid concentrated catechol-flavonoids, alongside inhibitors like rhodiola, silymarin, curcumin, and kava. They must also avoid direct dopaminergic precursors like L-dopa and isolated tyrosine. Prescribing these standard botanical extracts to a slow COMT patient can paralyze their already compromised clearance pathway, worsening both psychiatric and hormonal symptoms. Managing the slow COMT phenotype requires viewing the enzyme's capacity as a slow-draining bucket. To prevent an overflow, the clinical strategy must be synchronized across 4 phases. Phase 1 is stopping the overflow by eliminating external competitive loads. This includes removing catechol-flavonoids, heavy stimulants, and environmental xenoestrogens from the patient's intake. Phase 2 optimizes alternative pathways. Using DIM and cruciferous indoles shifts Phase 1 estrogen metabolism toward the safer 2-hydroxy path, while calcium deglucarate ensures these metabolites are excreted through the gut rather than reabsorbed. Phase 3 supports the enzyme itself by providing essential cofactors. Highly bioavailable magnesium glycinate, or L-threonate, is required daily to maintain the enzyme's catalytic function. Phase 4 spares the methyl donor pool. Supplementing with creatine monohydrate reduces the body's endogenous demand for SAMe, leaving more methyl donors available for COMT to process dopamine and estrogen. This multi-tiered framework shifts the focus from symptom management to the deliberate curation of the internal biochemical environment. Caution is required when managing the methylation cycle. High-dose methylfolate can trigger an over-methylation storm in slow COMT individuals. Methyl donors should be introduced in ultra-low doses, with vitamin B3 kept on hand to act as a biochemical sponge if irritability or racing thoughts occur. Targeted neurological supports like microdosed lithium orotate and L-theanine can help balance neurotransmitter excitation. When paired with autonomic regulation, like meditation, they provide the calm necessary for the prefrontal cortex to transition into sleep. The Val158-MET polymorphism represents a specific biological trade-off. While it limits the speed of recovery from stress, it enables the high dopamine state required for complex analytical work. When the biochemical environment is curated to prevent the bottleneck, this phenotype supports sustained executive focus and meticulous cognitive endurance.